So our next speaker is Rafael Fernandes, who will tell us about electronic correlations on the Quasicrystals.
Thank you very much. Thanks for staying until the end. I was told I have 45 minutes, but I'm only going to use half an hour. Tony, it's a great pleasure to be here. I had my connection with Tony actually goes back many 3 generations of physicists. Tony was advisor, as most of you know, of Amir Caldera, who is still a professor at University of Campinas, where I did my undergrad, master's, and PhD. Everything I learned from quantum mechanics was from Amir, so you can blame him for that. And Amir's student was Harry Westphal, who was also a postdoc of Tony here about 20 years ago, I guess. And I was Harry's student, so it's actually a recent picture of him, and I know everybody says, how come he looks younger than me? But let's not go there. Yeah. I think there's some Benjamin Button thing going on. But anyway, yeah, so it's a great pleasure, and I'm really looking forward to moving here and being around. So thanks again for inviting for this workshop. So this work was done, just want to highlight my postdoc, UC Zhang from Minnesota, and Richard Scalater from UC Davis, and is in preparation mostly because the paper is ready, but I still, anyway, you know how it goes. So I don't need to motivate Hubbard model for this audience, but nevertheless, this is a very good model to understand correlations. We know the 2 different limits and everything that happens in between when Hubbard U is much smaller, much larger than a hopping. And more recently, with advances mostly in experiments and also some theoretical progress, there's lots of focus on what's called flat bands, which is essentially when you send this hopping to 0. And then any small correlation, small in absolute values, will be important, and you can drive correlated physics. One material that, one class of compounds where this is very known is Kagome lattices. The same reason that in a Kagome you get frustrated magnetism, you also get, if you wish, frustrated nearest neighbor hopping, and because of that you get a flat band. Now, a lot of Kagomes are not metallic, but there are more and more metallic Kagomes found. One of the problems of the flat bands, or one of the challenges, is that most of the time, as you can see, it's somewhere usually very high in energy, especially for these compounds like 1 eV. So you really need to fine tune, and it's not always going to be possible. Then, of course, as we know, we have the twisted systems. And here, use the twist angle to tune this. It's not a really flat band in the most strict sense, but it's a very narrow band. This is actually results from Lucas, I think, right? That you can see here how 20, 40 MeV. But of course, you also need fine tuning because you need to choose this twist angle to a specific value. So this motivated me to look at a different system where you have flat bands, even though there are no bands, which is quasicrystals. And quasicrystals, in my opinion, is one of the most fascinating materials or things that come in physics. This is, again, a quasicrystal has no periodicity, but it has long-range rotational order. So this is the most perhaps known quasicrystal, which is called the Penrose tiling. It is just 2 patterns here that you can see, these 2 rhombuses that repeat in this pattern, even though it's not periodic. This is a representation of a more, let's call, realistic quasicrystal, in the sense that it's a 3-dimensional icosahedral quasicrystals. And as you can see, it's hard to properly see it. And for that, as Sheckman was discovered that in the early 80s, won the Chemistry Nobel Prize a few years ago. And if you read about quasicrystals, you will want to work on it, because there's nothing conventional about this. So the first known, there's a whole very interesting story of how they went after to find the first naturally occurring quasicrystal, which was then recently, it's recent because you can see there's a COVID, so it's recent. It was found to actually trace to an ancient meteorite. So anyway, lots of conspiracy theories, right? And it is actually more recognized that whenever you have some big explosion, quasicrystals show up. So they found one in a sand dune in Nebraska, produced by lightning strike, and also explosion in Trinity site. They also found the quasicrystals. So these are very weird and interesting. So it's always, yeah, well, yeah. So if you find an excuse, so if you find a reason to work on quasicrystals, I strongly recommend. But now into physics, you know, there is more and more evidence of interesting physics happening in quasicrystals. For instance, not that long ago, well, maybe a longer time ago, they found this quantum critical state in a magnetic quasicrystal, which is associated with some valence transition. Much more recently, the discovery of first superconducting quasicrystal was found. This is some alloy. Very recently, a few months ago, the group of Pablo and other people doing twisted stuff, they found out that you can create your quasicrystal by twisting. And that's actually a huge area where by twisting, you can actually, you can escape some of the restrictions of crystallographic restriction theorem. So there's also, you can have a Moiré quasicrystal. You can also do that in photonic lattices. So there's lots of properties in photonic quasicrystals. And there's even this, it's something I found very interesting. This is Kenjiro Gomez. And they found, if you remember, many years ago, the group of Hari Manoharan had found this way of using carbon oxide molecules to do artificial graphene. So you can do artificial Penrose tilings also using the same technique. Yes? Right. Good point. You just, yeah, you just, yeah. Exactly. Yeah, so it's high, exactly, yeah. There is a very well-defined recipe on how to create those, and it's just, so there is some interest of some physics, and as I mentioned, I think since this discovered superconductivity, people have been, again, there's always been interest in this field, but there's some surge. I'm just highlighting some of the papers talking about pairing or Mott insulators or Hubbard models. There are lots of questions, and it's an interesting and exciting field. So what I'm going to talk about is that quasicrystals actually have something quite interesting, and in hindsight, after you find the results, like, oh, why didn't I think of that before? Which is something that we call site-selective correlations. And there's some interesting connection with that and flat bands. So let me start by doing no interaction. I'm just going to do Penrose quasicrystals, and I'm just going to put, you're going to not see the Penrose, apparently. Sorry. Yeah, my screen looks good, but anyway, this is a different kind of Penrose lattice tiling called kite and dart. Instead of rhombuses there, just imagine kite and darts, or just Google it. It's going to take you 2 seconds. And if you just do a nearest neighbor models, this is a bipartite lattice. As you can see, you get a density of states that is asymmetric, and you see this huge delta function peak. Actually, 10% of all our states are zero energy. Of course, quasicrystals don't have periodicity. You shouldn't talk about bands. So when I say flat bands, and I use the quotes, is because I'm saying, well, if you have a macroscopic number of zero energy states, they behave as if it was a flat band. So I'm going to use this analogy, okay? And there's another Penrose lattice which you also cannot see, but you can Google it, which is the same one that I had before, which is called the rhombus Penrose tiling, or P3. And that one has a very similar density of states. You see, again, almost 10% of zero energy states, a little gap separating from the other states, okay? And so one thing that is interesting is to ask, okay, I have this quote unquote flat bands, and looking at these two density of states, you'd say they are the same thing. But it turns out they are extremely different. And well, it may be a hard talk to follow. You can, yeah, I don't know what to do about this, but anyway, you can sort of see it. Okay. So you can ask where the zero-energy state is coming from. So what you do, it turns out that these Penrose tilings are bipartite, and that's why it's particle hole symmetric. And it turns out that if I'm going to color with red, or I'm just going to color the sites that do not contribute to the zero-energy state. It's just easier. So it's the ones that don't give rise, contribute here. And I'm going to color either red or blue, depending on which sublattice it is. And you see they're all in the red sublattice. So this is actually a very trivial reason why you get zero energy or flat bands, is if you have a bipartite lattice, you have more of one sublattice than the other. That's exactly what happens here. And the only difference here is that this is a weird sublattice, but it's still the same physics, same effect. But now if you look at this other, which is called the rhombus tiling, you find out that in the thermodynamic limit, there's no sublattice mismatch. You have the same number of lattices, yet you get almost the same 10% here. Okay? And what you find actually when you look at where these excluded sites are, you find something very bizarre. You have some regions of the quasicrystal where the sites not participating in the zero-energy states are in the red sublattice, then they switch to the blue, then they switch to the red. So this actually has been known for a very long time about this structure, and you can exactly know these numbers, and of course there's some golden ratio, something there. But one thing that we're puzzled is how, I mean, two lattices that are so similar, have so similar density of states, why they look so different. And what we did here with my former student Ezra Day Roberts and my current/former colleague Alex Kamenev was to actually, and this is actually a simulation. This is not just a schematic. It is actually the result. You see a pattern of alternating between A sublattice, B sublattice, A sublattice, B sublattice. If you add them up, as you can see here, it goes to 0. But what we said, we realized that, yeah. So I'm marking the sites that do not contribute to the zero-energy states. If it's red, it means it's in sublattice A. If it's blue, it means it's in sublattice B. This is a small piece. And now I use something called inflation to just generate a very large lattice. And I continue doing that. Now, there's so many points that we're not really seeing much of the difference. I'm coloring the region according to which sublattice. If it's all blue, I'm going to color everything blue. If it's red, that's what I'm plotting. Okay? So it is kind of schematic, but generated from this. And so what we realize is that let me define a sublattice, a local mismatch. So I can define a mismatch between A and B as some coarse-grained, and that's why we color like this, some coarse-grained function. And then if we define like this, and we can actually use a recursion, just based on geometry, a recursive relation about this, we can actually get this exact number of zero-energy states. Yes, they are pinned at zero, exactly. Right. Only if yeah, that's a great question. Not really, because as you can see, there are these domains that separate them. So unless I turn on next nearest neighbor hoppings, that's preserved. Right, right. Yes, they're connected in these domain walls here. Yes, absolutely. But oh, you're asking whether I'm counting those? I'm not counting those. Sure. Here. Yeah, remember, these are the states that do not contribute to the zero-energy state. Yeah. You're right. If these were the ones that contribute to the zero-energy state, you'd have this problem, but they are isolated from each other. Yes. Yes. Thank you. No, they're either one or the other. And what happens is that there are these what we call domain walls that separate the regions where you have one and from the other. They don't talk to each other because these are the excluded sites.
And so the tails don't fall.
No, no. If they're absolutely confined to zero, they have to, otherwise you would not. Otherwise, you would not be zero in the states. Yes, absolutely. Oh yeah, absolutely. You know, I agree. And as you said, this has been known for, I don't know, almost 40 years. But the only thing we first thought this could be related to some topological properties, never were able to do anything about it. And in the end, what we settle for is that you can think of a coarse grain mismatch. And you can make the connection between these two cases as if one of them is like a ferromagnet, or you have a global lattice mismatch that is the same everywhere. Versus here, you can actually describe very well as if you have an anti-ferromagnet in the sense that you have a modulated structure. So if you add up the staggered sublattice magnetization, which is exactly this quantity here, you get the number of zero energy states. Now, your question is why? Why does that? I don't have a better understanding than reframing the problem in terms of some spontaneous breaking of, it's not really a symmetry, but in the spontaneous creation of these domains. Anyway, this is all now interacting, and we thought it was curious. And now what we wanted to do is, what happens now? So the lesson we learned from here is that flat bands, even though they may look identical in density of states, they actually can have extremely different structures, in this case, in real space, in materials that are periodic in orbital space. And we want to know if this could cause any difference when you turn on correlations. So to do that, we included Hubbard U, and we just did quantum Monte Carlo. There are many experts here, so I'm doing something very simple. We just do it half filling, because that's where the zero energy is. And we use open boundary conditions because we don't want to generate any periodicity. And we generate these tilings by a method called inflation, which is more benign than the other inflation. But in any case, that also restricts our ability to do finite size scaling, because I don't know how to do finite size scaling in terms of inflation generations. But in any case, Hubbard model has been studied a lot. There are recent reviews. I just put two here that were published in Numerics and Analytics of Hubbard model. I think Steve is in one of them. But we wanted to understand what is different when you do this in a quasicrystal where you have this site dependence. Okay, now you can see better. The first thing to notice is this is the rhombus tiling, is one of the two kinds that we have. You see that I have actually 5 different local coordinations of sites. And this is a generic property of quasicrystals, okay? So I highlight here, they have different colors. This one here, for example, has 5-fold coordination. This one has 7. This one here has 3. And we still have some with 4 and 6. So you already see one of the defining properties is that different sites have different coordinations. And there is a connection between this and the zero energy states. If I look at the zero energy states, what really matters is this one here is the spectral weight, if you wish, of each type of site to the zero energy states. And you find that the only kind of sites that contribute to the zero energy states are z equals 3 and a little bit of z equals 5. The others are never there. In other words, if I look at the red sites here, the red sites are all these excluded sites. The black ones are the ones that actually contribute to the zero energy states. You see that most of the black sites are z equals 3. And you may find 1 or 2 which is 5, but all the rest is red, meaning it doesn't contribute to the zero energy states. Okay, so now the same thing happens for this other, which now you can see better, the kite and dart tiling. There are 3 kinds of sublattice of coordination, 3, 4, and 5. And you can see that the zero density of states has contributions from z equals 3 and z equals 5. Mostly 3 than 5. All right. Oh, where are my data points? That's going to be hard. Okay, so it's beautiful data. Yeah, exactly. Okay, I'm not gonna make that joke, but let me just we look at a specific heat. So okay, so now this is results from one Monte Carlo. You can look at a specific heat, and at 0 U, you can see the characteristic going up and then down. Okay, you can see it. Great. See, this is a great eye test for vision. You know. I'm increasing U. Now you can start seeing. So what I'm plotting here is the. Thank you. Now they're going to fall asleep. Thank you. Let's see now if it's a bit better. No. So maybe now this is now the difference, okay? I'm looking at the difference between the specific heat at a finite U. This is U equals 2. And you see that it's not changing a lot. Now, oh, look, it's looking better, huh? You start seeing this enhancement at low temperatures, and at U equals 3.5, you see that the second peak appears here. Second because there was already an underlying broad peak, okay? This is known from several works on Hubbard model, quantum Monte Carlo simulation. Huh? Quantum Monte Carlo. No, because I'm at half filling. It's a bipartite lattice, so I'm good. Yeah. If there was a sign problem, I would be doing it. Put this way. So you see this upturn, this peak here, and that's exactly, again, we're relying on previous works on Hubbard model. This is where you usually associate the Mott transition. It's one of the most precise ways, and you see here that you get, I'm going to associate 3.5. If I keep increasing U, this peak just starts becoming sharper and sharper, and you can see the data now. Look at that, U equals 6, and so on. And now, I didn't want to put everything together because it would be hard to see. You'd not believe me by looking at the curves, but there is the characteristic crossing point, which is seeing all this kind of Mott transitions here very nicely. And you can also look at the structure factor. And here, see, it's not as clear. You do see an enhancement, as you expect, but this is really where you can pin down that there is a Mott transition happening about 3.5. Nothing different than you do for a square lattice, actually. You would see something extremely similar, which is disappointing. Where is the new physics? Is there one? You do the same for, this is the other lattice, tiling, I'm sorry, the kite and dart. Again, same structure. So then we decided to look at local properties instead of global properties. So what we did was, let's focus on the rhombus tiling. And let me look now at what I really wanted is the density of states, local density of states at its sites. That's not really completely clean procedure. So instead, we rely on this trick that was introduced here by Nandini and Mohit many years ago, of using this quantity here, which is we just call spectral weight. It's just a proxy of the density of states. And we just did here at U equals 0 to show that indeed this is the density of states. And as you can see, if you have a finite density of states at zero temperature, which is the flat band signature, this doesn't go to 0. The other ones go to 0. So these are the 5 different sites that we have. So now what we're going to do is measure this WZ, this spectral weight, as function of temperature for the different kinds of sites. Okay? So this is the one for U equals 2. Again, nothing really changes much with respect to the one that I showed, the no interacting. You see the Z equals 3 is the lightest one. It has the highest spectral weight. And it goes equals 3, 4, 5, 6, and 7. It goes in this order, which is the same order essentially as you see here. Okay? But now let's keep increasing U. Now you see I passed at 3.5, which is the global Mott transition. Now all the curves bend down, right, and tend to go to 0 because I have presumably an insulating state. But you still, I hope you can see, and here plot there's a 1/t just from the definition of this quantity. So here we multiply by t. And I hope you can see that we still have the same hierarchy. Small z has large spectral weight. Large z has smaller spectral weight. But now what we observe is that if we keep increasing that, did you do it from there? Okay, good. But what you start seeing is that as I start increasing, I don't know how to make it stop. Done. Okay, good. You now see here at this u, there is a line here which you cannot see, but I hope you, I hope you can see. Can I use my startup to buy a new? Anyway, I hope you can see now that you can see clearly from this. Well, you could see. I will invite you to come here if you don't believe me. You could clearly see there is a crossing below a certain temperature, which here is about 1, where you started having the z equals 3, having larger spectral weight, to having smaller spectral weight now. You switch the hierarchy. And as you keep increasing this, I think it's going to become more and more clear. And I think this here, now you can see very well that below this line here, and here I think is a little more transparent, the hierarchy changed here. Okay? And this is what we call site-selective correlations. What is really telling us is that the sites that have small z are being more strongly affected by correlations than the ones that have larger z, because of this changing hierarchy as they start increasing u. And this actually, there's some recent real space DMFT calculations on the doped Hubbard model, and they also see some site selectivity in where the doping goes. So we think this is related. And if you plot actually this T star, this crossing temperature, you see, we know here is very hard. Sometimes I look at the plots and I say, oh, there is a crossing. Sometimes I look and I say, I don't see a crossing. So I don't know what's going on here. But you see very nicely that there seems to be a connection between the global value of u, where you see this Mott transition, from this T star, this crossover temperature. How do we understand that? Why smaller z seems to be more strongly affected by correlations? If we had a periodic system, it would actually be easy to understand. In a periodic system, the bandwidth is 2z times t. So the smaller the z, the smaller the bandwidth, you need a smaller value of u to get a phase transition. And that actually is what they see. For example, this is very nice data. This is in a cold atom system where they could switch the lattice from triangular to Kagome, and they have different coordinations. And they saw that the critical value of u, these are bosons, it's a little bit different. So it's a Hubbard model for bosons. And they saw that it scales as u over zj. It's a mean field scaling, completely a mean field argument. But at least in the Bose-Hubbard model, it seems to work. But of course, here, I can't do this argument because I don't have a periodic lattice. These are really local properties. So yet the same intuition works. The smaller z, which happens to be also the ones that give rise to the contribution for the zero energy states, are the ones that get more strongly, the spectral weight gets more strongly suppressed. Okay. Now, to show, and I'm almost done, to show that this actually, we wanted to see, again, this is a proxy for the density of states. So we did something that I understand is illegal in some countries, which is called analytical continuation. And what you find is that those general trends are seen here. We couldn't really see that the Mott transition happens at different temperatures in different sites. That we don't have that resolution to say that. But you do see that the sites with the smaller z have a large gap appearing. Funny enough, usually it's the sites with a large z that show that Kondo peak, which is a more mean field-like behavior. But then at lowest temperature, the gap open in all of them. And we actually, if you plot what is the value of the spectral weight at zero frequency, you see there's lots of scattering here, but you see that for small u, the higher values come from the z equals 3. For larger u, the higher values come from z equals 7. So this is just to show that there is this site correlations. We call it like that, and I'm going to finish here because of this. It somehow is reminiscent of what the orbital selective mode transition, in the sense that in orbital selective mode transition, you have different orbitals that have different hoppings. And when you have different hoppings, they can undergo mode transition if you wish at different values of U. It's an oversimplification. You need also Hund's coupling. Here, somehow, because of the local Z being different, you get the sites being affected by correlations, the spectral weight associated with that site, the local density of states being more strongly suppressed than others. So I'm going to just say that the same happens for the kite and dart, and I'm going to leave you with my conclusions. Thank you.
I'm more experimental. You mentioned the paper by Ken Goals, where they did.
Yes. Sorry, I didn't say who else. Thank you. Yes.
But then, when they constructed part, but the days can you real space pointing out, but the same density states.
They do. But my recollection is yes, but they had a kite and dart lattice, which gives the trivial structure, if you wish, the one where you just have on the same sublattice. My recollection is that they could manipulate that by applying magnetic field, but I have to remember. But no, they did that for the kite and dart, and there is a non-trivial structure.
This means that the red sites would have a larger dynamic spectrum.
Sorry, go again.
Dynamical spectrum in excess of 2x.
Right.
And so, since the red sites are the ones that contribute to the zero glass,
Mm-hmm.
well, they are,
Right.
they would be the ones that piece that out. If you look at that, right? But there shouldn't really be any.
Yeah.
We're saying that these sites are affected, so
No. I'm not. This evolution is the same as the half filling Hubbard model. There's the transfer. This is just U. There's nothing. The dopant that I mentioned actually, but you're right that there was this paper here that I mentioned where they did very recent paper where they did. Now you cannot do quantum Monte Carlo away from half filling, or you can, but have sign problem. But then they do see, and I'm trying to remember now which way it goes, but they do see that when you would dope it, the dopants go essentially to this equals 3 site, I believe, which I think is more or less what you're saying, that's where the dopants go, where you have the largest correlations. Okay. You just lose. Actually, it's funny. This is very stable. You can apply magnetic field. You can do actually random. You can do Anderson model. This still remains there. The moment you put a next nearest neighbor hopping, this is essentially gone. So the zero in the states there are no zero in the states anymore. Yeah. Yeah, I mean, you're going to see some spectral weight here in the middle, but this delta function, I believe it's just, of course, it's always discrete. So you see a bunch of spikes, but you don't see these like macroscopic at 0, It's not that they shift, it just kind of gets, maybe that's what you meant by dispersion, just gets trickling, yeah.
Structure because can be obtained by projection from 5 dimensions.
This one is, yes, 5 dimensions, that's right. 4, actually, this one. That's an excellent question. We thought about it. It turns out that we couldn't get any new intuition by doing this, except that what we realized is that there is one periodic. Yes, we tried to count the zero modes in this first paper that I mentioned to you. We tried to do that. We didn't really get any new insight. One insight we got is that if you go, this number here is about 10%. You can ask, is there any quasicrystal that gets higher than that? So we did something simple. We started with a 3D lattice and do a cut. And it turns out that the highest number of states is for a periodic lattice, which is the dice lattice. That actually comes from a projection, it's a commensurate projection of higher dimensions. But there you always have, for any unit cell, an extra site, and that gives you a huge peak. So I don't know. I didn't see any connection there. So I don't know.
I'm sure your bottom slitter isn't just the nail and the pyramid.
We didn't see anything that would look like an antiferromagnetic order. Yeah, I had it somewhere here. We see the enhancement, but we don't see. No, this one was actually, yeah. This is it doesn't look anything that you'd associate with a phase transition.
Shouldn't be a phase transition.
Right, but there's nothing that would indicate any crossings or anything that would indicate that you were going through. It actually looks exactly the same as you do in a square lattice Hubbard model.
Okay, that's exactly what I'm saying. Square lattice Hubbard model has a nail grants.
Sure, but why? But that comes because you have a Mott insulator.
No, there's no such thing as a Mott insulator. But
okay, wait. Let me. Steve Kivelson. No, I see your point. How would you disentangle that? What would you?
So, so ground state is an antiferromagnetic. You can also understand your different. Start from viewing this infinity limit. The charge fluctuations that occur in T squared over U. Right. They're going to occur more on the sites with bigger coordination than smaller.
Right. Exactly. Oh, you're saying that I should think in terms of a J that is T squared over U, and then T. Sure. I mean, yeah, but I don't see. I mean, for this level, the two I'm at low temperature. No, there's no frustration. You can get near order. But again, sure, but how is this different than what happens in a square lattice?
My point exactly.
Okay. But then
you see antiferromagnetic.
Not on a square lattice.
On a square lattice,
There's a gap in antiferromagnetism at all of you.
I guess the question is whether there's a crossover or a transition.
Yes, exactly.
oh, this is most likely a first order transition. At 0, yeah. Oh, that's just based on all these previous works on QMC on at half filling. If you start increasing U, that you get let's see.
On the square lattice,
No, the square lattice, it's right, but the square lattice is special because you have the perfect nesting. Here, I don't have that property, right?
Yeah, but you are seeing a critical value view.
Right.
So then the question then is, what does that represent?
I don't think
I think more than
Perfect. Another way to say that it's bipartite.
Sure, true, but again, I see one signature in the specific heat.
Infinite density states. So you start from small,
Right.
you expect order almost.
But we don't see that, right? Okay, of course, we have a finite size system, but we need to increase we just see one signature of one peak in the specific heat, one crossing. These are properties of, I mean, at least that you can associate only with the Mott transition, not with the antiferromagnetic. This crossing of all the specific curves at one point, this comes back to these papers here. So I see where you're coming from, and I don't disagree with you that if I start at a strong coupling, if I think in terms of exchange, there's going to be different. I just don't.
Okay, so yeah, I'd like to see how it's different from the square lattice.
Oh, it's not. The glow. Oh.
So then the question then,
Okay.
what is
is going on that you see here.
If you do, okay, well, again, this is a finite size calculation. You're not going to see anything. It does because it's right. That's exactly what I'm using as my diagnosis to call it a mod transition. No, but from the quantum Monte Carlo simulations of other models, not sure. The Volhard paper where they talk about this comes from the Z infinity. Yeah, but again, if you do quantum Monte Carlo of all, you also get this. You get the same kind of crossing here. So the argument was this is a generic property. Now I hear you. I know that we have the expert here, so maybe you can. Since you've done this quantum Monte Carlo simulations, I don't see any signature of antiferromagnetism picking up anywhere other than just an overall enhancement. And yeah, they seem to saturate, but I wouldn't. This to me doesn't scream as antiferromagnetic. There is a lot. Specific heat is the worst quantity that we measure. Yeah, clearly I can't make a case that there is one crossing or several different, very close crossings. Yeah, it could be not. Yeah, that I agree.
So I'm curious on that on the right. What is the difference between U equals 3 and 4? I can't tell which.
Well. Right, that's why I plotted, that's why this was the idea of these plots to show the difference. And then you can see that 3, it continues increasing. And then for above 3.5, you see the second peak appearing.
Are you sure it doesn't, it's not peak out lower?
Oh, there could absolutely be. Yeah, I don't know. Yeah, sure. I don't know what happens. This is the lowest temperatures we can get. Sure.
So would you call this peak a crossover temperature or?
Oh, I see. So you're saying that, well, maybe my T star, my maybe just continues going exponentially small as I go to 0. Sure, that's an option. If that's what you're, Steve, if that's what you're referring to, I cannot tell which way it goes. I cannot see that because. Yeah, it's very similar. You're right. So sure. In this regard, you could think of, again, I cannot go below. I think here was beta equals 25. I think was or 20. So I don't know. Could be something below there, sure. But I'm drawing again. If I were to show you the square lattice, you probably wouldn't see any difference in the global property. So if that one you consider that, sure, this is another one. I agree.
Well, if you were to do the same calculation on the square lattice, your ABC, you needed quantum Monte Carlo.
I think this goes back to Edwin's question. I would, yes, that's what people have assigned. But the question is it because I'm not seeing, it all depends on this extra peak showing up. And I think his point is maybe there's an extra peak below the temperature that I cannot see. I can't answer that question.
Well, we'll talk about it when you get there.
Sure.